would be more clear for you, that's like regarding the grams and how it is transmitted. Yeah. In the what? So we are not, if you are asking, we are not transferring that. No, 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 you don't need that. You don't need transfer whenever you are having like max and, for example, milliliters. You don't need to. So just you need to know the connection between these, okay? How they are connected to each other. The clearance, concentration, volume, and plasma concentration. So final was our like 5 milliliter in minutes, right? So we just put it there, numbers, and we understood what was it. So we can calculate clearance of anything like that with the basic knowledge. Okay, let me see what's next. And okay, now we need to know our, like we know the clearance, right? How the materials are filtrated from the kidneys, and how to calculate that. But we also need to know the blood flow, renal blood flow, right? So mostly, if in the body systems you in the cardiology, I guess you already studied that 20% of the cardiac output is given to the renal blood flow. Yeah, so it is like the normal that we all know, and is directly proportional to the pressure difference between the renal arteries and renal veins, and it's inversely proportional to the resistance of the renal vasculature. So vasoconstriction of the renal arterioles, which lead to a decrease in renal blood flow, is produced by activation of sympathetic nervous system and angiotensin II. And at a low concentration of the angiotensin II, we are having like constriction of the efferent arterioles, and that's why we are somehow constricting and maintaining our GFR. Regarding the ACEs, I will not talk about this on this chapter. So whenever we're having vasoconstriction of the renal arterioles, meaning that it is done by two ways, either a sympathetic nervous system or either the renin-angiotensin-aldosterone sister by the constricting these smooth muscles here in the arteries, right? Like two stuff. Regarding the vasodilatation of the arteries, we are having like prostaglandins like E2 or I2, bradykinin, nitric oxide, and dopamine that are dilating our arteries. So according to that, whenever we're having like increase of vasoconstriction or decrease on the or increase in vasoconstriction or like dilation, we can control how many blood is going to the Bowman's capsule, meaning that we kind of can control how many, what is the rate of the clearance. Now question? just as into preferential constrict efferent arterial, yeah.
So the pressure in the arterial they increase.
With the at the low constriction, no, not. See, whenever we're having low constriction of the efferent arterial, it is protecting, increasing the GFR, meaning that I will go back. So, as I mentioned, it is all working on the afferent and efferent arterial, right? So whenever we're having a constriction here, the blood pressure will rise here, but not in this part, right? Minor constrictions, as I've said before, it is happening in the efferent arterial, right? And when we're having minor constrictions, it is maintaining the pressure here, but it will be decreased there. Got what I'm telling? Yeah. So one thing I will add. So whenever we're having constriction here the pressure is high, right? It is increased, right? It is increased, right? The pressure here. So whenever we're having constriction here, we're having increase in pressure, right? So meaning the GFR, glomerular filtration rate, will be high because more pressure, you are filtrating more. So that's what they are saying. You don't understand something. Can you repeat what you're saying? Maybe I will. Yes, because they are mentioning here the renal afferent arterioles. So that's what I'm telling you. That when we're having here some kind of constriction, no blood is entering the glomerular filtration, like no blood is here, so renal blood flow will decrease. That's what they are saying. Okay? Clear. Let's continue. Also, we're having like atrial natriuretic peptide, which causes vasodilatation with the prostaglandins, bradykinin, and nitric oxide of the efferent arterioles, and lesser extent they are having like vasoconstriction of the efferent arterioles. So overall effect that we might have, it is our ANPs increasing the renal blood flow. Okay. So we are having the autoregulation of the renal blood flow, and it is happening by the changing resistance in our vascular system. So if arterial pressure changes, a proportional change will occur with the renal vascular resistance to maintain the constant renal blood flow. So, for example, renal flow remains constant over the range of the arterial pressure from 80 to 200, and this is called our autoregulation. And we are having two processes how the autoregulation can happen. It is myogenic and tubuloglomerular feedback. So let's first discuss like myogenic mechanism. It is in which renal afferent arterioles contract in response to the stretch. Thus, increased renal arterial pressure stretches the arterioles, which contract and increase resistance to maintain constant blood flow. Is it clear? And the second one, it is tubuloglomerular feedback. in which increased renal arterial pressure leads to increased fluid next to the macula densa, and macula densa is sensing that we are having increasing overload and starting to release the renin, and we are starting renin-angiotensin-aldosterone process, and meaning that we are having construction in afferent arteriole, meaning that again we are having increased resistance to maintain constant blood flow. So thus, to summarize, we are having here like autoregulation. It is to maintain our normal blood flow throughout the renal arteries and capillaries, and we are having two mechanisms: myogenic, which is currently working about like the muscles and constriction, and we are having tubuloglomerular feedback, and it is done by macula densa. Okay, so we need to measure renal plasma flow, right? And we're having different injected materials like creatinine or para-aminohippuric acid, by which we can measure how much urine or how much stuff was how much was cleared, or how much renal plasma flow was. So PAH, it's para-aminohippuric acid, and it is both filtered and secreted by renal tubules. So we are filtering, and at some point in the tubules we are having like the secretion of that. So clearance of PAH is used to measure mostly renal blood flow, and clearance of PAH measures effective renal blood flow and underestimates true renal blood flow around by 10%. And here we're having formula for that, and we see here that C PAH, it is clearance of the PAH. Then we're having urine concentration of that, volume, urine flow rate, and plasma concentration of the PAH. So this is our formula for that. And we can add the numbers there whenever we will have it, and multiply and divide on that. Okay? Another formula that mostly we're using in the clinics, it is like the renal blood flow multiply, like it is renal PAH flow divided on 1 minus hematocrit. So meaning that's how much hematocrit we're having. We should measure that, and we can just 1 minus hematocrit. So we should know that denominator in the equation 1 minus hematocrit is the fraction of the blood volume occupied in the plasma. Okay? And the most important topic. Do you have questions regarding that? No. And now most important topic that we're having, it is GFR. In the clinics we're mostly using the GFR, and it is like glomerular filtration rate, and it is measured by the substance inulin, because inulin is one and only substance that it is filtered but not reabsorbed and neither secreted by the renal tubules. So the clearance of inulin is used to measure the GFR with this equation, and GFR, it is like glomerular filtration rate. Then we are having urine concentration of the inulin multiplied of the urine flow rate and divided on the plasma concentration of the inulin. So, for example, whenever we're having a case, inulin is infused in a patient to achieve a steady state plasma concentration of 1 milligram on milliliter. The urine sample collected during 1 hour has a volume of 60 milliliter, and an inulin concentration is around 120. What's the GFR? Right? So what we're doing, we're writing this formula, and as we had, inulin concentration was 120, and it is like urine concentration We wrote it here. We multiplied on the plasma volume of 1 hour next to it and divided on our plasma concentration of inulin. So it was this one. So we calculate that and we got that GFR is 120. Okay, questions? No. Okay. We are also having the creatinine and blood urine nitrogen, which are mostly measuring in the clinic, right? So now we should connect like the GFR with blood urine nitrogen and serum creatinine concentration. So BAN, it is like how many urea nitrogens are in the blood. However, it should be filtrated fully. And serum creatinine, it is the final product of our muscle degradation, and it is fully cleared from with the kidneys, right? So we should not have it in the blood. So BAN and serum when we're having increase in blood urine nitrogen and serum creatinine in the blood, like high levels, it means that GFR is decreased, meaning that the kidneys cannot filter that, so we are having it high levels in the kidneys. That gives us several diseases, and it can be caused by one of the diseases, which is called pre-renal azotemia, meaning that we are having pre-renally high level of nitrogen. It can be also caused by hypovolemia, meaning that we're having increase in the BAN more than in serum creatinine level. So we're having increase in the BAN creatinine ratio, and it will be more than 20, like BAN concentration. Okay? And also regarding GFR, GFR decreases with the age, although serum creatinine level is remaining same during all ages if we won't have like decrease in muscle mass, right? So idea of this is that creatinine level after some age, in the geriatric medicine it is raising up at some point because GFR is decreasing. Okay? Questions regarding this? Yeah. It is constant. However, if we're having, for example, Kwashiorkor or some Kwashiorkor, it is protein deficiency, malnutrition, like meaning that we're losing some muscle, then we might have like decrease in the creatinine level, because creatinine, it is the degradation material of the muscle, and that's why. It can remain also constant. I'm telling you that this is the extra cases when it is like no muscles at all. Okay? So, for example, during the malnutrition, we are losing proteins, and meaning at some point our muscles are degrading. So at some point we will have high creatinine, and then we're having no creatinine at all. Okay? Another point that we should know, it is filtration fraction, and is the fraction of the renal blood flow filtered across the glomerular capillaries. And we're having, like, it's a combination of two stuffs. It is like the GFR and renal blood flow. So normally filtration fraction, it is 0.20, it is like 20% of the renal blood flow that it is filtrating. The remaining 80% leaves the glomerular capillaries by the efferent arterioles and becomes the peritubular capillary circulation. When we're having increase in the filtration fraction, produces increase in protein concentration of the peritubular capillary blood, which leads to increased reabsorption in the proximal tubules. And whenever we're having decrease in the filtration fraction, produce decrease in the protein concentration of the peritubular capillaries blood and decrease the reabsorption in the proximal tubule. So filtration fraction actually is guaranteed, and we can measure how many, if it is increased or decreased, and how many proteins and other nutrients we are reabsorbed, or like will like increase and decrease in reabsorption. It will be more correct to formulate like that. Okay? And it depends proportionally to the GFR and proportionally with the renal blood flow. So another, like despite that we know that formula for the GFR, also if you remember, we have the Starling forces, right? The hydrostatic and oncotic pressure that exist in our vessels, and they are playing a huge role in our GFR and determining GFR, right? So driving force for reaching the glomerular filtration is a net ultrafiltration pressure across the glomerular capillaries. And filtration is always favored in glomerular capillaries because a net ultrafiltration pressure always favors the movement of the fluid out of the capillaries, right? So normally it will be located like that, as you see. So to understand this, we are having the formulation, so GFR, KF, that pressures, and we are using this formula for that. So to understand this formula, we need to know several materials. So we need to know the capillary hydrostatic pressure and oncotic pressure. So first of all, we are having constant coefficient of filtration coefficient for the glomerular capillaries. And as I mentioned, glomerular capillaries consist of the capillary endothelium, basement membrane, and filtration slits on the podocytes, right? And they are creating our Bowman's capsule by which we are filtrating materials. Normally, we are filtrating materials that are not charged at all. It will be more easier. However, anionic glycoproteins line the filtration barrier and restrict the filtration of the plasma proteins, which are also negatively charged. And that's why this is the basis why the proteins are not filtrated in the Bowman's capsule. If we're having some kind of glomerular diseases, the anionic charge of the barrier is destructed and removed, and thus we're having proteinuria, and this is the basis of the nephrotic syndrome in the pathology of the kidney. So to calculate that, like this coefficient, we need to know the capillary hydrostatic and oncotic pressure, as you see here, right? So this is our afferent arterial, and this is afferent, right? And as we see, this is the Bowman capsule's hydrostatic pressure, that it is always forwarded to the arterial. Glomerular capillary is vice versa, and also oncotic pressure of the capillary, it is like negative, right? So PGC, it is glomerular capillary hydrostatic pressure, and it is constant along the length of the capillary, and it is always increased by the dilatation of the afferent arterial or constriction of the afferent arterial. Yes? So meaning that when we are dilating the afferent arterial, more blood is going there, and when we constrict the afferent arterial, we're having like more pressure in the Bowman's capsule, so more can be filtrated. So thus we can say that glomerular capillary hydrostatic pressure is increasing the net ultrafiltration pressure in GFR. So this one is creating the capillary pressure mostly, and it's made important thing to have like the ultrafiltrate. Another one, it is like the Bowman capsules hydrostatic pressure, which is always staying the same in the capillaries, and we can increase this by constriction of the ureters. So increase in the Bowman space hydrostatic pressure, decrease the net ultrafiltration rate and the GFR. So as you see, it is vice versa, right? And if we constrict somewhere there, it is increasing that. So we are giving the idea that we are having high level of the filtrate in the Bowman's capsule, and that's why we don't need more to do that. So this is decreasing the GFR rate. Next one we are having, it is glomerular capillary oncotic pressure. It increases along the length of the glomerular capillary because filtration of the water increases the protein concentration of the glomerular capillary blood. So when we're having increase in the protein concentration, it decreases the net ultrafiltration rate and the GFR. And talking about like the Bowman capsules capillary pressure, it is usually 0, and in all cases it is ignored because like unless we don't have any filtration of the proteins. So this is normally idea how we're having the filtration processes by Starling forces. And let's do the sample equation of the ultrafiltration pressure with the Starling equation. So at the afferent arterial end of the glomerular capillary, we're having glomerular capillary hydrostatic pressure around 45, right? And we're having the Bowman capsules pressure hydrostatic 10. Oncotic one, it is 27. What the values and direction of the net of ultrafiltration pressure? So net pressure of this one is calculated like that, right? So we just need to put the numbers, and it will be +8, right? And meaning that it is in favor of the filtration. So whenever it's like this way, it is like this way, it is like in favor. That way, it is like not in favor, meaning that we're having reabsorption. Do you have any questions regarding this? No? Okay, so this is like the summary of what I've talked about regarding the filtration stuff. So whenever like we are having here filtration fraction, GFR and renal blood flow, right? So now we need to know what they are doing, like what processes can affect this. So whenever we are having constriction of the afferent arterial, meaning that less blood is entering in the glomerular capsule, we are having decrease in the hydrostatic pressure, right? Decrease in renal blood flow, of course, and filtration fraction, there will be no change, because like filtration fraction, it is like GFR divided on this. It is low, it is low, it is will be 1. Okay? Constriction of the afferent arterial, meaning that we are having more blood in the glomerulus than it is coming out, so it will be increased, that will be decreased, and by formula is the filtration fraction is proportional to GFR, meaning that it will also increase. Increased plasma, meaning the proteins, it will be decreased because we are having the capsule proteins decreased. Renal blood flow, no change, so this will also decrease according to the proportional formula. Uterine stones, it is like the ones that are in our ureters stuck there. So we're having decrease in GFR, no change in the renal blood flow, so again filtration fraction will be decreased. Clear at this point? Okay. And if you got everything, let's have a question. Yeah, one question and that's it. Actually, this is like a question from the USMLE UWorld 2022 Physiology. So, a researcher is studying the effect of various manipulations on kidney blood flow and glomerular filtration. Which of the following is most likely to both decrease renal plasma flow and increase filtration fraction? Yeah, the answer is C, of course. Constriction of the efferent arterioles. So why? This is like the schematic view what we've studied already. So whenever we're having constriction of the outgoing, like the efferent arteriole, will impede blood flow through the kidneys, right? This will decrease renal blood flow and increase the glomerular filtration. So again, problem with this glomerular basement membrane, right? So what's again renal plasma flow? It is same as renal blood flow, right? So in these photos, I was mentioning, these are explanation. I won't go into the explanations real deeply, but like renal blood flow, it is like same as filtration. So whenever we're having some kind of constriction, then like efferent arteriole, meaning that we're having this process going there. So we increase the GFR, but we decrease the renal plasma flow due to the efferent arteriole constriction. Okay, so that's why you need to remember this table real well, because in all exams this will come. Okay, on this we finished our today's class. Thank you for attention. If you're having any questions, feel free to ask. Okay, yeah.